All right, good morning and welcome everyone. I'm PeterLippmann. Some of you know me as their tutor. I am a PhD student in the group of Professor Hamprecht, who cannot be here this week. And yeah, this is why I have the honor of giving the lecture today. The topic of the lecture will be equivariance. That is how to build symmetries into neural networks, which has become quite a big topic in the machine learning world and is one of the key concepts in geometric deep learning. In particular, for machine learning in the natural sciences, equivariance is a very important topic because there you often have exact symmetries which play an essential role for the dynamics in your system. You have already previously encountered the concept of equivariance in this lecture here and there. For example, when you talked about convolutional neural networks, you said that they are approximately shift equivariant. Or when you looked at the transformer architecture, which operates on sets of inputs, at least if you don't use any positional encoding, they are perfectly permutation equivariant. But today we will look at a different kind of equivariance, namely equivariance with respect to the Euclidean symmetries, which is also a very important symmetry group, which includes the rotations, which we will focus on most actually, but also translations and reflections. And the aim of today's lecture is to give you an idea what equivariance is exactly, why it is a useful concept in machine learning, and also how to build equivariant neural networks in practice. When it comes to building symmetries into neural networks, there is quite a bit of cool theory, which is the reason why it can also get a bit technical. I will try my best today to give you a rather lightweight introduction to the topic, which hopefully helps you to build some intuition for it. Okay, to start, I want to give a bit of motivation on why one would look at equivariance. And for that, I want to look at a few quite simple examples which should illustrate how we traditionally do scientific computations and scientific predictions. So the first example which I want to look at is the angle between two directions. So the picture for this could look something like that. We have one vector which points in this direction, v1, and then we have another vector which points here, v2. And then the way how we would compute this angle here would be probably by using the following formula. We know that the cosine of the angle between these two directions is given by the dot product of the normalized vectors. So that would be v1 dot product with v2 and then divided by the norms of the respective vectors. And as you can see, in order to really carry out this computation numerically, we need to define a coordinate system. So in order to express these two directions in terms of numbers and then carry out the dot product, we need a coordinate system. Okay, that much for the first example. This is rather trivial. Next example, it's also quite simple still, is to compute the volume of a box. So the picture for this could look something like that. We have a box here in 3D with length A, B, and C. And then in order to compute the volume, we use the formula which we recall from school, which is just we multiply each of these lengths and therefore we get the volume. Okay, so far so good, but actually what we're really doing is we're taking the integral. I mean, if this were a more complicated object, we're taking the integral over the indicator function which is 1 everywhere where there is the box and 0 everywhere else. And again, in order to write down this function, we define a coordinate system, and then we integrate over all of space. So yeah, what you will see is that if you choose an appropriate coordinate system, you will get out this very easy formula. But there might be some coordinate system in which getting this indicator function is substantially more difficult. For example, my handy, I think my phone here, this is a good approximation for something like a box. If I would align this with the coordinate system, it's really easy to write down this indicator function. But if it's somehow misaligned and somehow positioned arbitrarily in space, this makes it much more difficult to carry out this computation numerically. So we see that some coordinate systems will make this computation easier than others. But, and this is a very important point, in general, the choice of this coordinate system is arbitrary. But choice of coordinate frame is arbitrary. And this means that results from different coordinate frames must be consistent. And exactly this consistency is, for a very intuitive definition, equivariance at least with respect to the symmetry group with which you're focusing now, with respect to Euclidean symmetries. And yeah, what we've seen so far is that angles, volumes, also distances, they are invariant quantities, so they do not change, like the numerical outcome of the computation will not change if we change the coordinate system. Another physical example for this would be the kinetic energy. The kinetic energy of a particle, which would be 1/2 mv squared. This, given that it's an invariant quantity, is also called a scalar. And how can we see that this is a scalar? I mean, what do we mean when we write v squared here? Really, we mean v squared to be the squared norm of the velocity vector. And then this, if we would write it out not in components, but as vectors, would look something like this, v transpose v. And now if we apply a rotation, if we rotate our coordinate frame by some rotation r, what we will get will be rv transpose rv. And then we can write this out as V transpose R transpose R, which is just the identity for rotation matrices. V, and therefore we see that this object is invariant. Okay, let me give a last, again, quite simple example, which will be the acceleration. So formula for this would be we sum up the forces acting on a particle to get the total force, and then we divide by the mass. And now if we apply a rotation here, again, some rotation by which we rotate the coordinate frame, the coordinates of the forces will change actually as the coordinates of the velocity changed here, because these objects are vectors. Also the A will therefore be a vector. So what we will get will be, in the new coordinate frame, we get sum of the forces rotated by this rotation matrix, and then this is nothing else but the rotation applied to the acceleration in the old coordinates. So what we see here is that the coordinates of vectors, they change under rotation of our coordinate frame, meaning that you can have the same force or the same velocity as a geometrical quantity, it's the same, but described in two different coordinate frames, they will have very different coordinates. And this behavior of how objects, how geometrical quantities transform under rotations, this brings us to the notion of group representations. So much for the motivation. This should show you how, the concept of equivariance is related to how we traditionally do numerical computations based on physical laws, for example. And now we will look at formal definitions for group representations. Group representations, I will write reps for short, for representation, group reps, and equivariance. Okay, who here did have some bit of group theory during their studies? For example, when they looked at particle physics or quantum mechanics, Lie groups, Lie algebras, representation theory. Okay, at least a few. I will nonetheless start with a recap first with the notion of a group. To start very basic, what is a group? Just to recall this, a group G is a set of elements. With a binary operation which is closed. So if you take two elements from the group and then you do this operation, you still end up being in the group. And this operation is typically called the group product. With group product, such that, so this group product should fulfill the following properties: that if you first take the product of A and B and then take the product with C, it should be the same thing as if you first take the product of B and C and then the product with A. So this is called associativity. Then the second condition is that you have an identity element, which if you take the product with any element of the group, it will not change this element. So this is the identity property. And then there's also the property that for every group element, you have an inverse group element, which if you take the product with it, it will give you the identity element. And this should hold for all of the elements in the group. Okay, this is what we need for the definition of group. Then we can continue with the definition of a group representation. So I write again rep for short, group representation, row of a group G on a vector space V is a map row which maps from elements of the group to the invertible matrices on that vector space, such that this map fulfills the following condition, that if you look at the product of two group elements, it should be the same as the product of the representations of the individual group elements. So in here we have the group product, which is the product between A and B, and then here in this space, the product between these two objects would be the matrix product. This should hold for all elements. And this map, when it fulfills this condition, one says that it respects the structure of the group, and this is also called a group homomorphism. Group homomorphism. All right. That's the definition of a group representation. Maybe we look at a small example for this. So the symmetry group which we are interested today would be the group of the orthogonal matrices, which are all matrices which fulfill the condition that the transpose of a matrix is also the inverse of that matrix. And then there's also a subgroup of that group, which is the special orthogonal group, which are elements of OD, which also fulfill that the determinant of these matrices is 1. And this means, this constraint that the determinants are 1, means that these matrices should be orientation preserving, and this is the group of rotations. And this here is rotations and reflections. And we have already seen two representations of this group actually, namely scalars, as we had them before, scalars. For example, the norm of a vector, this will be a scalar. As we've seen, if we apply some rotation, what we will get will be the norm of the rotated vector. But this, because norms are preserved, distances and lengths are preserved under rotations, and in general under orthogonal transformations. This is why we have we get out the same result again, and then this is just a single number. So the vector space in which or on which this representation acts is a one-dimensional vector space. 1D vector space. And the other example that we've already seen are vectors. So for the case of the velocity, for example, we saw that if we apply a rotation on this velocity, we get out the rotated vector, and this is a non-trivial representation which acts on the three-dimensional Euclidean space. And the representation for this, one could say it transforms under rho of R equals R. So in this case, the representation are the matrices themselves. And up here, what we get is that rho of R for the scalars is just always the identity for all R. This is also called, we want to squeeze this in somewhere here. This is also called the trivial representation. Trivial rep. And here for the vectors, we have a non-trivial representation, acting on this three-dimensional representation, on this three-dimensional vector space. These two groups which we have defined here, the orthogonal and the special orthogonal group, sometimes you will also see equivariance with respect to ED or SED. Then this means the Euclidean or the special Euclidean group, which we get if besides rotations and reflections, we also include translations. Okay. Do you have any questions so far? Okay, all good. Then we continue with the formal definition of equivariance. So, given a group G and vector spaces V and W with representations rho V, which is the representation how the group will act on the V vector space, and OW, the representation how the group will act on the W space, then a function f, which maps between these two vector space, is equivariant. Exactly if it fulfills the following condition, namely that if you look at the action of an element from your rotation group, sorry, I'm going to do this more general here. I'm going to call this element G here, and this acts on the output of a function. This should give you exactly the same as if you act on the input of the function, like this. So on the input, we have to use the V representation to act with the group element, and on the output, we use the W representation. So this should be fulfilled for all X in the input domain and for all group elements. Then we call function equivariant. And intuitively, this means, like I said, that one obtains the same result if one transforms the input of the function, or if one applies the function first and then transforms the output of the function. Or in other words, you could also say that an equivariant function is a function where the output will transform in a well-defined, predictable way if we apply a transformation to the input. Okay, then there's one more special case about this. Special case that is f is invariant. an invariant function if this representation on the output space is just the identity for all group elements. So this means that as we apply some transformation, like a rotation, for example, to the input, the output will just stay the same. Then we call the function invariant. Okay, and as we've seen previously with these examples, physical laws they are equivariant algorithms. For example, if we look at example 4 here, we see that the ingredients which we give to this algorithm, if we want to compute the acceleration, is we give to it all the forces acting on this particle, and we also give the mass of the particle. And then we basically put these as inputs, and then we get the acceleration as output. And if we just apply the algorithm, what we will get is something that is consistent no matter how we choose our coordinate frame. So physical laws are designed such that if we basically use them as algorithms for numerical computations, that they are equivariant. And this is also the big motivation of why, if we want to mimic physical laws, for example, with a neural network, why we would want to make it equivariant, because it should exactly fulfill this property. But the problem is, of course, there's a problem. Standard neural networks, they are not. They are not equivariant. For example, we could look at the following function. Very simple network. We look at the ReLU as a nonlinearity. Could actually use any other nonlinearity, but just for this example here, we look at the following function. Then if we now look at the following inputs, for example, let the input x be given by force 1, force 2, and the mass, to really now mimic this algorithm of computing the acceleration on a particle. Then what will happen, a fully connected layer, as we've written down here, fully connected layer will mix the components of the vectors of these forces here, will mix them arbitrarily. Which is bad, at least for equivariance. Because if, for example, we would take a linear layer which looks something like this, like we take one weight for each force vector, then this would give us again a vector as an output, and this would be equivariant. But if we do something like this, we have a weight for each component, which would naively happen here. So for the first component of the force, and then of force 1, and then for the second component, and so on. This will in general not be equivariant. I mean, it could learn in principle that in order to be equivariant, these three weights here should be the same, kind of to recover this case up here. But in general, it will not do so. And yeah, and furthermore, there's also the question, I mean, if we look at a layer like this, then we have not yet included the mass. right? This would be a computation which preserves the vector property, but the mass is a scalar, so it's still a non-trivial problem how to include the mass here in this computation. Okay, so this much for motivation of why standard neural networks are not equivariant. Okay, I mean, one can even say one more thing, actually, namely the component-wise ReLU this will, of course, also not preserve equivariance. Component-wise ReLU also gives problems. Yeah, I'm going to sketch this in a very sloppy way. So if I apply the ReLU to a vector, I'm going to now draw the vector, which would be like this is the coordinate frame here, and there's a vector in this coordinate frame. I said it would be sloppy. It gets a bit worse now because I'm also sketching here that I want a 180-degree rotation applied to this vector, and then afterwards apply the ReLU. So what we will get is we will apply the ReLU to something like this vector here, which has all negative components. It's something like -1, for example. And then what we will get out, if we apply the ReLU component-wise, we will get 0, 0. But if we now, to check if the ReLU would be equivariant, we do it now the other way around. So we first do apply the function, first apply the ReLU on this vector here. And then we do the 180-degree rotation. You can already see what will happen is the ReLU, the component-wise ReLU, will not do anything to this vector, which has only positive entries. And then afterwards we do the rotation, but for sure the result will not be the 0 vector. Okay, so standard nonlinearities are a problem, and also standard linear layers are a problem if we want to have an equivariant neural network. That's bad news. But there's hope. So we will look at simple ways first to achieve equivariance. Okay. Arguably, the most simple thing you can do, I mean, there will be, I guess there are more examples of simple ways how to achieve equivariance. I will present 2 examples to you, and arguably the easiest thing you can do is data augmentation. Data augmentation. What is data augmentation? It means you apply a random element from the group to which you will want to be equivariant every time you encounter a sample during training. This is how you do data augmentation. And there are many things which are cool about this. One thing is that this will be very easy to implement. It works with any neural network, so you don't have to put any constraints on your neural network architecture. And in principle, this also works with any group. One thing that you have to maybe take care about is that if you apply this group element to the sample, you should not, like, depending on the input and the target which you have, you cannot only apply it to the input, but you also have to apply it to the target. For example, if we look at this setup here where we want to predict the acceleration, then we will have to, if we apply a global rotation, we will have to rotate these forces as the inputs, but we also have to rotate our target, the accelerations. But this is really the only thing you have to keep in mind. And then, okay, what is the downside of data augmentation? The downside is that the equivariance has to be learned from data and that it will not be exact. It will only be approximately equivariant. I mean, if you would train it perfectly with infinite amount of data, perfect optimizer, you would recover exact equivariance. If you also have a function space which is large enough to have perfectly equivariant functions in there, but yeah, in general, what you will end up with will only be approximate equivariance. This is data augmentation. And then another conceptually simple way of achieving equivariance is global canonicalization. So what you will do in this case is you perform all of your neural network computation in a global coordinate frame in which the sample is canonically oriented. Okay, what does that mean? I'm gonna draw a small sketch. So for example, if you want to build a classifier on faces to say whether they're happy or sad, then your input may look something like this. If it's presented to your neural network in a random pose that is not yet canonical, but then you can choose your coordinate frame such that the face will be oriented canonically. So if the face were, for example, oriented like this instead, then you would do all of the computations in this coordinate frame. And if you do it like this, you always ever have to, with your neural network, learn to do the right computation in one coordinate frame. And you always do your computations in this coordinate frame. And like that, you achieve equivariance. I mean, first you will achieve invariance by basically factoring out the global orientation of your input. But what you can do is, if your output is not a scalar, then you can rotate back afterwards. Okay. And one thing to note at this point is that global rotation of the coordinate frame is equivalent to global rotation of the input. So I will sometimes use this interchangeably. If you rotate all of the objects in the world, or if you rotate your coordinate system, this will give you kind of the same coordinates. So this will be equivalent. I mean, with one rotation in the one direction, you have to do the rotation in the other direction. But yeah, in principle, these two views are equivalent, like rotating the face such that it's pointing like upwards, or choosing a coordinate frame, like rotating your coordinate frame such that in this coordinate frame, the face is canonical. This is the same, kind of. Okay, again, advantages of this method are that it's conceptually fairly simple. It works with any neural network architecture. So again, you do this before you apply any of the neural network computation and then possibly afterwards. So the neural network, you can use whatever you want. It may be possible to achieve exact equivariance with this, but the difficulty of this method obviously lies in finding or computing this canonical frame. Sometimes it might not be possible to find a canonical frame due to symmetries or some other problems. And in some cases, there are canonical frames, but they are just hard to compute. Like you would need a neural network kind of to predict the canonical frame, and then this neural network would have to be equivariant such that your frame prediction is equivariant and will rotate if you will rotate the input, because this is what a canonical frame should do, right? And then if you need an equivariant neural network to come up with this canonical frame, which is a very non-trivial problem, then you might already use the equivariant neural network to just predict the thing that you actually want. Okay. Good. Do you have any questions while I wipe the board? Yeah? Okay, so the question is, the representations which we look at right now, they are linear in the sense of that they map to linear elements, right, to invertible matrices. And how about nonlinear representations? Yeah. So I think the way why we want this linearity is in order to actually fulfill this group property. I think this is... Yeah. No, I think not really in practice, not that I'm aware of. So you mean to not act on a vector space? I mean, this vector space need not necessarily be the Euclidean space. The way that we are constructing it right now, it is, but it can be any general vector space here. I'm not quite sure I understand the question. Maybe we discuss it in the break. Is that okay? Nice. Okay, any more questions? Okay, then I actually think it's also a good time to just take a break. We continue shortly before 10. Yeah.